The relationship between, we throw these words around a lot, but you got to get it straight what they all mean. Zeros, factors, solutions, and x-intercepts. What are they? How are they related? They almost mean exactly the same thing. This table summarizes it. I think this shows up in the book in section 6A. Okay, so if we've got, that looks like a mess, but if we've got some polynomial is all that is. If f of x is some polynomial, that's a really ugly way of writing it. But we all know what a polynomial means. Then these statements are all equivalent. A zero, k is a zero of the polynomial function if k is a value that we plug in and get back 0 for an answer. So that's equivalent to saying that x minus k is a factor. We've dealt with that, right? We said if we have a 0, subtract that from x, and that's always the factor that goes with that 0, right? That's like saying k is a solution of the polynomial equation f of x equals 0, right? In other words, if we put k in for x, we get 0 back. That's what a 0 means. And then the last thing is the x-intercept part. But the x-intercept only applies if it's a real 0. So if k is a real number, k is a real 0, then it shows up as an x-intercept on the graph. And we talked about that also. But I think this chart's good because it puts it all in one place. So that's in 6.8. It's in your book. PowerPoint will be up on the website. There it is. Okay, now 6.9 is the last section in Chapter 6, and it does something interesting. Okay, there's two parts in this. I'm only going to talk about one of them today. Okay, this has to do with. Yeah.
I bet you said no more 6 after the last one.
There's one more section. 6.9 is it.
Okay.
Sorry, I lied. There's one more. 6.9 is like the application section. There's nothing really new in it. It's just the same stuff as before. It's just how do you apply this to real world problems. Okay, so here's what you can do with this. If you're modeling with polynomial functions, there's a couple ways you can think about this. All the regressional stuff that we've done in the past, to make a long story very, very short, all the regressional stuff applies just like it did before. For example, if I pull up a calculator.
Hey, Mr. Oya, how'd you get that shirt?
I got this shirt from a friend of mine who coaches, and so he gets tons of this stuff. So I get a lot of it too. If I go through the stat menu, I go stat, calculate. Remember that we used to do, there's linear regression, right? So if I put in a bunch of data and I want to fit it to a line, I use linear regression. We also just learned that if I want to do, from Chapter 5, we learned that if I've got a bunch of data and I want to fit it to a parabola, well, that's quadratic, so I use quadratic regression. Now, there's some other options here, too. Look, there's cubic regression and quartic regression, and then that's as high as this calculator goes with polynomials. But cubic just means a third-degree polynomial. Quartic just means a fourth-degree polynomial. So we can do polynomial fits just like we did for parabolas. We can do that for cubic functions and quartic functions. And so that's kind of the Chapter 6 version of what we did in Chapters 3 and 4 was linear. Chapter 5 was quadratic, and so this stuff would be our regressional equivalent for this chapter. Okay? Now, there's one other little piece that I want to draw your attention to, and this part's a little more complicated, so you got to be absolutely with me on this, or you won't get it. But if you do, you'll get it, and it'll be done. It's not that big a deal. It's called finite sums. Okay? Now, this stuff we know how to do. We know that if we want to do a cubic function that goes through those points, we just do regression, okay? And I'm going to skip through that one. You guys can figure this stuff out. We know how to do regressional stuff. That's not a big deal. Okay. This is the one I want to show you right here. Okay. We want to come up with. I want to show you something. I want to show you that if we have a polynomial function that is a third-degree polynomial, we want to show that the third-order differences are constant, finite and constant. Okay, now what do I mean by that? By the differences, we mean the difference in the y values as I move up incrementally from x equals 1 to x equals 2 to x equals 3 to x equals 4, etc. If I calculate the y values that go with those, the differences are just how much the y values are changing from one x value to the next. So for example, if I want to find the difference between the first two, I'm just going to subtract the y values. Going from 6 to 25, I always subtract the left from the right. 25 minus 6 is 19. In other words, the y value increased by 19 from the first term to the second, right? From the second to the third, the y values increased from 19 to 45, right? Adam. Good. So, and how do we get those y values? Plug them in the function, right? If I put 1 in for x, I get back 6. If I put 2 in for all those x's and calculate, I get back 25, etc. That's how I'm getting the y values. I'm just evaluating the function at those values of x, right? And so I'm just going to calculate all these finite differences. Now, there's a ton of room to make mistakes on this. You got to be careful. What happens on these problems a lot, on the test also, is that people do all this work and they make one or two little mistakes and it screws the whole thing up, right? So you got to really take your time and be careful with these. 70 minus 25 is 45. 153 minus 70 is 83, etc. Now, those are the first order differences. Obviously, those are different. They're not constant. Let's find the second order differences. Okay, same process again. 45 minus 19 is 26. 83 minus 45 is 38. 133 minus 83 is 50, etc. Right? Third order differences. Now this time, look what happens. They're all the same. Okay? So here's a property of polynomials. If I have a polynomial, whatever the degree of the polynomial is, that's the order of the differences that are going to become constant. And then after that, they just would be 0, wouldn't they?
What does that mean?
Well, what this actually relates to is taking derivatives in calculus. But that's still a couple years away. But that's where this actually comes from. Now, we can use this relationship to our benefit, though. Okay, here's how we can do this. What if we have a problem like this? If we have this data that we want to fit to a polynomial, right? So we know that f of 1 is negative 2, f of 2 is 2, f of 3 is 12, etc. We're given all this data. And we want to figure out what's the polynomial function that fits this data. Here's what we can do. We can just go through and, well, we could use a calculator. Right? I just told you that we know how to put this data into a calculator and do a polynomial fit, and it'll tell us what the answer is. But I want you to see something here. Watch what happens. If I pull this calculator up, how am I going to do this?
I think you should do it on the calculator.
Okay, so if I pull the calculator up, I'm going to go to Calculate, Edit. Let's put this data in, okay? So the first order pair would be. Okay, I've got a lot of people talking here. It's really bugging me. I'm going to ask you kindly one more time to just not talk. Fake it or actually pay attention. You decide, but don't talk. So 1 goes with negative 2. Okay, negative 2. 2 goes with 2. 3 goes with 12. Etc. Right? But now, and I can keep going with that. Let me put in just a little bit more. I want to show you something here. So, 4, 5, and then I got 6. Okay. And 4 goes with 28. What's the next one go with? 50? 78. Okay. Okay, so if I were to go, let me turn on this first stat plot here. Let me get rid of that guy. Turn on the first stat plot, and I go zoom stat. There's my data. Okay. If I want to know which polynomial fits that, I could try them all. I could try every one of them. If I go stat, calc, and I do a quadratic regression, quadratic fit. Okay, if I go down, And I'm going to store it. How about, let me do that. Store it as y1. Or as, yeah. Oh, sorry. Nope. Forgot I did. What did I do wrong? Calculate. Oh, I know what I did. 5. I got to store it. Oh, yeah, I go alpha F4. Yeah. Store it as y1. Calculate. And look what happens. I get our perfect fit, right? Perfect fit. If I graph this thing, because it said r squared equals 1, so that's 100% fit. So it goes through all those points. Okay. Now watch, if I pick a third degree polynomial, it's also going to work. Okay. So stat, calc, cubic regression. So I'll do 6, and I'll put that in as y2. Perfect fit. If I look at them side by side, there's the first one, there's the quadratic, there's the cubic. They look almost identical.
Wait, what number can you put in there?
I put in all these numbers, all these ordered pairs.
Where are you good to get it to graph? Like, I guess the.
What's that?
Yeah,
good point.
You would have caught me for a half a second.
Oh my god.
Where do you get to? The half a second.
To graph? You got to turn on the step. Yeah, get rid of that.
She turned
I was just
You want to bring it out of
I was just giving you crap and then
You just didn't go like this.
Hey, you can't talk.
Shh. You got to turn on flat water.
420.
Okay, so but anyway, back to what we're talking about here. Now, when we're doing a polynomial fit, we want to find the smallest polynomial that fits, right? So there's a couple strategies we could do. We could just try all the polynomials and see which ones fit. Caesar, get rid of that, please. That could be time consuming. Or we could do this. You knew the or was coming. Yeah. Okay, we can do this. We could determine exactly what the degree of the polynomial is, which tells us what kind of regression to do. Okay, we could, if we do the finite differences stuff here, watch what happens. Okay, we'll see. If I find the first order differences, 2 minus negative 2 is 4, 12 minus 2 is 10, etc. Second, subtraction. Always subtraction.
All right.
Second order differences are constant, so it's second degree, right? So then that means we know that if the order is 2, it's quadratic, and so we would use quadratic regression. But we also know something else. If it's quadratic, now if it's a second degree polynomial, how many points determine a parabola? But let's 3 do, right? And we can remember, easy to remember that is if you start with a line. 2 points determine a line, which is a first degree polynomial, right? The power of x is 1. 3 points determine a quadratic, where the power of x is 2. How many points would determine a third degree polynomial? 4. Always one more than the degree, right? So how many ordered pairs do I need? I only need, in this case, I only need 3. Because it's second degree, I wouldn't have to put all this data in. I could just save some time and only put in 3 ordered pairs. If the degree had been, 4, I would only have to put in 5 ordered pairs. Does that make sense?
Yeah.
Okay. So that's how we know by doing this finite difference trick. That's how, if we start with the data, that tells us what the degree of the best fit polynomial actually needs to be. Yes?
So like the points on like F1 is -2 and 4, is that the point?
You mean, where does this come in?
Yeah, like what
Okay, because we're subtracting the y values. So we know, see now, f of 1 equals 2. So let me do something here so you can see this better. So this is the first, we could call that y1, right? That's the first y value. If I put in f2 for x, there's my second y value right there.
So then the 4 and the 10, 16, those are the x's.
You subtract the
The 4 and the 10, no. Those are actually not, what those mean is kind of weird. Those are just the differences in the y values. So we call these are the first order. First order differences is what that first row is. Okay, so it's the differences, meaning subtracting the y values, right? 2 minus negative 4, 12 minus 2, 28 minus 12, etc. And then these would be the second orders. And if I had to keep going, the next would be the third orders. Okay? Yep.
Alright, so if there's 5 ordered pairs that you put in, does that mean it's quadratic?
The fact that I put in 5 was more than I needed. It wasn't efficient.
No, I mean like you said, you had 4 ordered pairs and you.
Okay, no, that's how many I need. How many I need? I need at least 2 ordered pairs to determine a unique line. I need at least 3 ordered pairs to fit a parabola. So in other words, I couldn't put in 2 ordered pairs and ask the calculator to do quadratic regression. If I did that, it would blow
Yeah,
up.
but you said like if you needed 5.
Right, just need it.
No, put that away.
So
So
you needed 5 to be quadratic then?
if it was quadratic, I'd only need 3. Right? Because the quadratic would be second order. Now I did 5 because I just put them all in to begin with, but I didn't need to. If I had done this first, I would have known that because it's second order, that means I need second order means 3 ordered pairs. So I could have just taken those 3 and forgotten about those. Right? Just to save myself some time. I wouldn't have had to put all those in my calculator. Right? If the first order differences had been constant, it would have been linear, and I could have just taken 2. That's all I would have needed. 2 points defines the line, determines the line. Okay? Does that make sense? Sort of, kind of, maybe. I think you got to try it a little bit. You're gonna have some questions. But
Yeah, how would you enter it?
in the calculator? Oh, the answer. Yeah, the answer. So the answer would be, okay, so then what we would do here on the calculator, I got to drag it over. So the answer is this. We would have gone to calc, quadratic regression, and then just...
Well, I'm trying to figure out what the answer would be.
So there's the answer. So the answer then is, it's going to be y equals, a is 3.
Oh, okay.
So it's going to be 3x squared. B is negative 5. So negative minus 5x, and C is 0. So that would be it. 3x squared minus 5x. Yeah, good question. I should have said that. Yeah. Okay?
Makes sense then.
Okay? All right. Let's go try it.
Trying to do it around me, you go.